A vector. Regardless of what it's representing, a vector, its length always represents the magnitude of the number, and the arrow, the direction you point the arrow in, represents the direction it points in. So velocities, for example, we've drawn vectors to represent velocities. If I have a vector, its length would represent however fast the object was traveling, say 5 meters per second in this case. The direction, since my arrow is pointed to the right, the direction would be right. Or in the positive x direction, as far as a Cartesian coordinate system is concerned. Okay. If I had a vector of 10 meters per second to the right, I would need to draw it twice as long. When a vector lies along an axis, we say that it only has one component. So if we're talking a traditional coordinate system, Cartesian coordinate system, these vectors lie along the x-axis. So both of them would have only x components, is what we would call it. The components, we always break them down according to the coordinate system we're using. Each component, we're going to have a component parallel to our x-axis and a component parallel to our y-axis. For example, if our velocity was 5 meters per second at an angle of 40 degrees, we can say 5 meters per second at 40 degrees, and that's a perfectly valid way of writing our vector. There's nothing wrong with that. That's, if you remember polar coordinate systems, the polar coordinate system was always a radius and an angle. You can write your vectors that way. There's no problem with that. But we can also write them in terms of components. When we talk about components, we're saying that it has a piece that's parallel to the x-axis and a piece that's perpendicular to the x-axis or parallel to the y-axis. This would be called the x component of our vector. This would be called the y component of our vector. We can write our vectors in terms of the components. We could easily find these too, since we know the hypotenuse and we know the angle. The x component is the adjacent side, so the cosine of 40 degrees is going to equal this x component over the hypotenuse. So x, our x component, is going to be 5 meters per second times the cosine of 40 degrees. That's our x component. Let's see if my calculator works. The y component, it's opposite our 40 degrees, so we have the sine of 40 degrees is equal to y over 5 meters per second. So the y component is 5 meters per second times the sine of 40. So we could describe our vector as an x, y value. How far does it go in the x direction? How far does it go in the y direction? That is another perfectly valid way to write it. When we write it that way, we call it vector notation. By this way, this one's called magnitude and direction. The magnitude is the 5 meters per second. The direction is the 40 degrees. Vector notation is when we write it in terms of its components. Now, to write it out, we use what are called unit vectors. A unit vector is a vector that has a length of 1. No meters, no seconds, no anything, just 1, just the number 1. And it points specifically along an axis. If it points along the x-axis, we use an I. To represent a unit vector, we use a little hat, a little caret above it. That little caret tells us that it has specifically the length of 1. If it points along the y-axis, we use a j. If it points along the z-axis, we use a k. So to write our answer in vector notation, we would say our vector was 5 meters per second times the cosine of 40 degrees. That's the number, the numerical value of the x component. And then we would write an I hat next to it to mean specifically that points in the x direction. So this is the x component, and it points in the x direction. The I hat is telling us that it points in the x direction. Plus, how much in the y direction? 5 meters per second sine of 40. And we would write a j hat on there. So this is the magnitude. The 5 meters per second sine of 40 is the magnitude of the y component. The j hat tells us what direction. That's the y direction specifically. So this is vector notation. It gives us each individual component and what direction it points in. In this case, since we're not doing 3 dimensions, we don't have a z component. So if you want, you could write plus 0 k hat, if you really wanted. But there's no need to write that, since 0 is 0, it just means there's no k hat. Okay. What would be different? If instead of pointing to the right and up, we pointed to the left and up. Would this still be true? No. It still has a length of 5 meters per second, yes. But it's not at 40 degrees. Remember with polar coordinate systems, where was the angle always measured from? X-axis. So we could write it in terms of magnitude and direction, 5 meters per second. We're having a hard time remembering our angles. What's the angle between there and there? Subtract 40. Fabulous. It's okay, it's been a while. Now, when we draw in our components need to get us from one end of the vector to the other end of the vector by connecting the dots, basically. One of them needs to be along the x-axis, the other one needs to be along the y-axis. It doesn't matter which one you draw first. You can draw the x one first or the y one first, it doesn't matter. If I draw the x one first, there's my x component. I meet up, there's my y component. Please keep in mind the components always meet at a right angle. The vector itself is always the hypotenuse. It's a general rule. So this side is still going to have a length of 5 meters per second cosine of 40 degrees. Because we'd still use cosine 40, is this side over the hypotenuse. This side is still going to have a length of 5 meters per second sine of 40 degrees. But how are we going to change the vector notation to now implicate that it's not pointing to the left and up, but sorry, that's the right, to the right and up, but instead is pointing to the left and up?
Change the signs.
Change the signs. So the cosine one's pointing to the left, so that we'll put a negative 5 meters per second cosine 40 with the I hat, so that we know it's negative I hat, plus the 5 meters per second sine of 40 j hat. So the magnitude and direction is 5 meters per second and 140 degrees. vector notation is the negative 5 meters per second cosine 40 I hat plus the 5 meters per second sine 40 j hat. Turns out anything that is a vector, whether it be position or velocity or acceleration, or we're going to get to other quantities, forces and momentum, other things that are vectors as well, we treat them all the same way in terms of breaking them into components. So once you know how to work with vectors, you use them the same way regardless of what type of vector you're working with. Okay?